So I'll start recording. Actually, maybe I want this to be a little bit further away. Good. So let's say what we achieved last time, right? So last time we said the following. We said, let's look at so we said, okay, we had some tight binding model of an insulator. Okay? And then we did a computation. We computed that there should be some edge current. Do you agree? That there should be edge current that is proportional to the following quantity. It is the integral over the Brillouin zone of my curvature, which was something like the integral over the Brillouin zone of the exterior derivative of my connection over the Brillouin zone. Do you agree? And this connection, not xi, ki. And this connection was defined like this. We had some coefficients for some particular band, right? Sum over alpha of u alpha k, partial k u alpha k, dk I. K partial I. That's right. Okay. Do you agree? We had this kind of expression where these u alphas, these were the coefficients for the kind of we're looking at specifically the lowest band. Do you agree? So this is the lowest band. Okay, and this was this is proportional to this quantity we called the Chern number, right? C. So the lowest band, which we wrote in some basis. This was some atomic orbital basis that we got from the tight binding model, and then these were the eigenvectors. Okay, and so this is what we computed, that there should be some current which is proportional to this Chern number. Okay, and we realized that this has to be an edge current, so it has to be on the edge. Why? Because we realized, well, in the bulk my system should be periodic, so in the bulk it should be an insulator because the Bloch bands have a gap. Do you agree? The Bloch bands have a gap. So in the bulk, I have to be an insulator. So this current has to be, on the edge, right? And what this really was, this was maybe the Chern number is like 1/2 pi or something. That I'm not sure. But what this really was, this is, remember, we were computing the expectation value of some Wannier orbital at like a momentum 0 and momentum 2 pi. So this is at m equals 0, 0. Right? We did some like partial Fourier transform, right? And then subtract and then compared it to 0 momentum. Okay. This is what we did last time. Do you agree? We computed this expectation value of like the position of some Wannier state at k y equals 0 momentum versus 2 pi momentum, got that that's equal to this quantity, and realized that, wait a second, this is, you know, the position, the expectation value of the position of some state before and after something happens, and it seems like, you know, if this is non-zero, then it looks like that state moved, so I should have had some current. Okay? Do you agree? Very good. Okay. And so, where does the geometry come in? So, all right, so recall that this, that the connection was some one form on the Bloch bundle. Do you agree? So I had my, I had my Berlin zone, which was a torus, okay? And then above this Berlin zone, what did I have? I had my Berlin zone, but at every point, I attached a vector space where I would only include the lowest band. Do you agree? I'd only include the vector of the lowest band. Okay, so this is lowest band. And so we got a Bloch line bundle. Okay. And so this connection was defined on this Bloch line bundle. Okay? And so we got that, okay, if we got the following. If Bloch bundle was trivial, so what I write here is actually very much abusive notation, and I'm explaining why. So if the Bloch bundle is trivial, I have global coordinates. And so I can really define A to B on the Berlin zone, okay? And then by Stokes, the Chern number has to be 0, okay, by Stokes theorem. Do you agree? But this is if I can define global coordinates for this bundle, right? If I cannot define global coordinates, then I cannot define, like, take A and kind of define it over here. Do you agree? Because you know, dA is defined kind of at every point on the it's not just defined at every point on the torus, but there's also kind of points on the along the line as well, right? And as I go around, I can have some non-trivial connection which picks up a phase, and I can't define coordinates in a unique way, such that I don't deal with this kind of fact that I pick up a phase as I go around the torus. And so in that case, I cannot define A to be really, I can't define, I can't kind of pull back A onto the Brillouin zone. And so in that case, this, I can only define A kind of in local coordinate patches. I can onto the Brillouin zone globally. Okay, so I do so locally, and then that implies that C equals 1 over 2 pi over the Brillouin zone dA need not be 0. Okay? Because this A thing, I can't define it on the whole torus. I can define it. I can define it on a piece of a torus, and then I have an A. Then if I want to go to another part of a torus, I need to do some gauge transformation here, and then so that I can define it here, and so on and so forth. And so I can pick different coordinate patches over each of which I have A defined, and so I can compute this dA thing. And so I compute this integral kind of in different patches, and then that won't necessarily be 0, right? Because it's no longer, I no longer have an exact form. I'm no longer taking D of an exact form.
Is it not necessarily 0, or is it just simply non-zero?
It's guaranteed to be non-zero if I cannot define global coordinates. And so this is a fact that I do not prove. But the point is that this number C, it classifies line bundles up to homotopy. Okay, so the point is, if I compute this number, and I see that it's 0, and then I see it's non-zero, then I know that this this line bundle is non-trivial, and I can I can classify all of my line bundles up to homotopy just by computing this one number. I know what equivalence class it lies in. And so this kind of helps me achieve my dream of classifying the Hamiltonians, right? Because, if I have, actually, this is maybe not immediately obvious. This might be a kind of a difficult step to make, to say that if I can classify my line bundles with this, then I can also classify my Hamiltonians with this. That might be a bit difficult to get to, but that's the spirit of what this is trying to do. I don't want to say too much about this. Okay. Right. And so once again, whenever I write something like this is really abusive notation, because this A is defined over here, not over here. And so when I write something like this, I really mean I have some coordinate patch, okay? In this coordinate patch, A is defined over here, and then I can pull it back to somewhere over here in a nice way. And yeah. And I'm not even telling you kind of in what sense I pull this back. So this is very sketchy what I'm writing here, but I'm giving you a conceptual idea. We will not actually do this calculation. We'll find another way to guess as to guess something essentially, and then go for it. Okay. Yeah. But do people see why, if I can't choose global coordinates here, why this need not be 0? Actually, no. Do people understand why if I have global coordinates here, why this has to be 0? if I have global coordinates here, right, then if I have global coordinates, then this just looks like this line bundle just looks like T, the torus, cross C. Do you agree? And so then I have a differential form that's defined on this thing. Do you agree? And I can just project the project what this differential form onto the onto the torus. So I only plug in stuff from the torus into it, and then that gives me my differential form. And this means I get a globally defined differential form on the torus. Okay, but if I have a globally defined differential form on the torus, then taking d of that and integrating it over the torus has to give me 0, because just by Stokes' theorem, right? Because by Stokes' theorem is d of a has to be equal to the integral of a over the boundary, but the torus has no boundary, so it has to be 0. Okay. Versus here, when I do d of a, I mean if I don't have global coordinates, that means this thing looks only locally. It only looks only locally like the torus, like some bit of the torus cross C and some bit of the torus cross C. Do you agree? And in each one of these, I can kind of do this thing where I define the connection in these coordinates and then pull it back here, right? But then this means I kind of have a different differential form in every coordinate patch. And I can still integrate it over all the different patches and add up the integral and compute this in some sense. But this is no longer truly d of some globally defined differential form. Okay, does this roughly make sense? Like, this is no longer a differential form that's defined everywhere. This is really, I define it in different regions and then integrate it over each region separately. And so then it's not truly, now if you do Stokes' theorem, there is in fact a boundary because, I integrated over only like some patch. And that now there is indeed a boundary, and now this could indeed add up to something non-zero. Okay? Roughly the idea makes sense? Okay, good. But, okay, this calculation is actually, doing it analytically is like, okay, you can do it, but it's kind of hard to do because, look, if I don't have global coordinates, then I have to sit around and like pick different gauges in different parts of my, manifold. That's hard to do by hand. Okay. And there are numerical ways which kind of are easy to do that compute this. I won't talk about them. But what we want to do is we want to do something even simpler, right? I'm telling you that, this whole thing, this could be like non-zero, right? And, okay, well then, if I'm telling you that this is possible, I should give you an example of a tight binding model where this is indeed non-zero, right? I should do that. And so what we will now do is we'll try and come up with some tight binding model where this Chern number is indeed non-zero, but we'll kind of see it in a way that it's going to be, we're not going to actually compute anything. Well, we'll compute some things, but we'll instead try and go for defining something that gives me a non-trivial bundle, okay? And if you get a non-trivial bundle, then you know that, because this Chern number classifies the bundles, if you know the bundle is non-trivial, then you know that the Chern number will not be 0, okay? So right now what we're going to do is we're going to sit down and try and come up with some tight binding model in real space on a lattice that gives me a non-zero, that gives me a non-trivial bundle, okay? And the model we're going to come up with is going to be what's known as Haldane's model, okay? Very good. So, I guess I'll move this here. And then I'll keep writing on this board. This is nice. Okay. So goal come up with non-trivial tight binding model. So topologically, a non-trivial tight binding model. Okay, how are we going to do this? Well, so yeah, we're going to do this in the following way. Instead of working like this setup before, it was working with the block bundle. Do you agree? I'm going to try and do this a bit simpler. We're going to pick a Hamiltonian of a nice form and try and go back to this picture where we're looking at homotopy classes of Hamiltonians instead, and try and write down a Hamiltonian that is not in the same homotopy class as the identity Hamiltonian. Okay? So the identity Hamiltonian, so where it's just like ones on the diagonal for all momentum k, that's clearly going to give me a trivial bundle, right? Because what? Because this means on the Berlin zone, everywhere my eigenvectors are exactly the same, and so I can easily write that down as a trivial bundle. Okay, so what are we going to use? Maybe let's use this color. So some facts. You know, if I had identity of k equal to just 1, 1, 0, 0, this kind of Hamiltonian, this gives a trivial bundle. Do you agree? Because at every point in the Berlin zone, kind of the eigenvectors are always pointing the same way. Do you agree? And so the block bundle is just going to obviously be just T2 cross C, where C is just the second is just E2. So that's easy. I can just choose global coordinates directly. So then I want to come up with a condition. So I want to come up with Hamiltonian that is not homotopic to this one. Right? I want to come up with a Hamiltonian that's not homotopic to the identity. Okay, that's the goal. And so let's see how one can do this. Okay, what we're going to do is right now we're going to we're going to make a few assumptions. First of all, we're going to assume that we're going to work with a two-band model. So we're only going to have two states for every momentum k, two-band model. So restrictions. So assumptions. Okay. We're going to look at a two-band model. Okay. And we're going to assume that our Hamiltonian is of course an insulator. So H gives an insulator. So homotopy has to preserve the gap. Preserve gap. Okay. And I mean, we've said this before. Why are we looking at a two-band model? Because it's very easy to compute things with a two-band model, and people understand things that happen for a two-band model really well. So let's first, state some known facts about a 2 by 2 Hamiltonian. So first, So first, the claim is that any 2 by 2 Hamiltonian can be written as h of k dot sigma, meaning it can be written as h1 of k times sigma x plus h2 of k times sigma y plus h3 of k times sigma z. Okay, where sigma x, sigma y, sigma z are Pauli matrices, where so sigma x 0, 1, 1, 0, sigma y 0 minus I 0, sigma z is equal to 1, 0, 0 minus 1. Okay?
Why is the trace always 0?
Oh yes, you could add a constant term. That's true.
Oh, okay.
So this is up to constant term.
Okay.
In principle, you could extend this to a 4 vector and have sigma 0 be the identity.
Yeah.
And that's right. Okay. Very good. H of k is now a function from the torus into R3. So h's are real numbers, and then sigmas are Pauli matrices. Okay. This is just for now, take this as a fact. Any 2 by 2 self-adjoint matrix can be written as a linear combination of sigma x, sigma y, sigma z with real numbers. Okay. You can just check this. You take a self-adjoint matrix, you know how it has to look like, and then figure out what the coefficients should be. And you can check that they have to be real numbers. Okay, very good. And so now, you say, okay, very good. What do I want? Oh, yeah, and I guess in our case I want... So these are some useful facts. One useful fact is that the eigenvalues of h of k dot sigma are plus minus the norm of h of k. This is just, once again, you can compute this. So h of k is now it's this vector, okay, in real space. Okay, do you agree? So one thing. So if my thing is gap preserving, if my thing preserves the gap, what does this mean about h of k? If I always have a gap.
Never vanishes.
Yeah, that's right. If I always have a gap, right? That means that my eigenvalues, there's always some finite difference between the two eigenvalues. Do you agree? But I told you that the eigenvalues in this case are h of k are plus minus the length of this h of k vector. Do you agree? So if my eigenvalues are never equal to each other, that means that the only way the eigenvalues here are equal, if these are the eigenvalues, is when the norm of h of k is 0. Do you agree? So this means that if I have a gap, that means h of k is never 0. Okay? Is not 0 for all k. Do you agree? And so I want to come up with homotopies, only for where h of k is always non-zero. Do you agree? And In that case, let me separate this out. In that case, claim if I have a Hamiltonian h of k equals h of k dot sigma is insulating, meaning that there's a gap everywhere. This implies that h of k is going to be homotopic to the following Hamiltonian, to h twiddle of k, where h twiddle means I take h of k and then divide it by its norm everywhere. And then do that dot sigma. Okay? This is still a well-defined thing because, you know, when I say insulating, I mean there's a gap. Do you agree? And if there's a gap everywhere, that means that h of k is never 0, so dividing by its norm is okay. I'm never dividing by 0. Okay? So this is the claim. Okay? So remember, do you remember what homotopy is? So I can smoothly deform one Hamiltonian into another as a function of some parameter. So recall that, I'll write it here. Recall that h is homotopic to h prime meant that there exists some function f of t from 0 to 1 into Hamiltonians such that f of 0 was equal to h, and then f of 1 was equal to h prime, and f was like smooth or continuous, whatever you want. Okay, so there's like a way to interpolate with like some curve between h and h prime. Okay? And I'm telling you that if I have a Hamiltonian, then I can always that has a gap, then I can always smoothly deform it into a Hamiltonian that has that is defined by some like unit vector h of k. Do you agree? Do you see what the claim is about? Okay. This claim I can easily prove. The homotopy is I just have h of k dot sigma, but then I multiply it by 1 over norm of h of k to the power of t. Do you agree? And so at t equals 0, this is just 1, it's the same Hamiltonian. At t equals 1, I get the thing that you want. And then h of k is never 0 because it's I have the gap. And so that's very easy. Do you agree? Yeah. Does this roughly make sense? Okay. Actually, this is so this is a bit of a misnomer, because this Hamiltonian doesn't give a gap, right? So maybe what I really want to do is maybe put a minus on this, and this is going to be like sigma z. Okay, -1. But you know, it doesn't matter. Any Hamiltonian that is like constant. Any Hamiltonian that's constant should give me a trivial bundle. Sorry, that's what I meant to say. Yeah. So now, let's see what advantages realizing this gives us. Okay. So I now realize that this h, so this new, I now realize, okay, instead of studying h of k, right, let's study this, h twiddle of k, where now the Hamiltonian is always defined by what? Now h twiddle of k is defined by some h of k dot sigma, okay, where h twiddle of k, the norm of this is always equal to 1. Do you agree? It's always a unit vector. So I get that h of k is some map from the torus into the Riemann sphere. Okay? Do you agree? So now what I can do is I can say, I can just think of the Riemann sphere, okay, and I can think, okay, a point on the Riemann sphere defines like h of k, defines my Hamiltonian at the momentum point. Do you agree? Okay. And now, what do we want to do? And actually, just side comment, this is when people talk about the Bloch sphere, people are talking about like literally this. But okay, it's the Riemann sphere. But you know, it's the same thing. But okay, I'll go back. So what did we want to do? We wanted to find a Hamiltonian. We wanted to find a tight binding model Hamiltonian. Okay, that did what? That was not homotopic to a Hamiltonian that's just constant everywhere. Do you agree? Right, so I wanted to find a Hamiltonian that's not homotopic to something that's just constant at every point. Okay, and so how does a constant Hamiltonian look in this picture? Well, it looks like I take the whole torus, okay, and every point on the torus I map into just, some fixed vector. Right? Every point on the torus gets mapped to like one constant vector, and then that's constant Hamiltonian. And I realize that this is trivial. Okay, this should be the trivial Hamiltonian. Okay. Now suppose, okay, I'm going to erase that board now. Actually, I'll take a picture and then I'll erase it.
There should be a I in front of the connection.
Oh yes, yes, that's right.
On the left side.
Over left side here.
Yeah, here should be I.
That's right. Yeah.
I on the other side, or like negative I
On this side?
I think that's the convention.
Yeah, sure. I believe. Oh, sorry. Actually, I don't want to erase anything, but yeah. I should, in the future, I should do the opposite. I should start with the. I should start with the middle board, then do the top board, and then erase, and then have a third board. But I, for some reason, don't do this. Okay. Okay. So now the new goal is the updated goal. side so that it's easier for the recording a bit. But so current goal, we'll find condition for Hamiltonian not to be homotopic to a constant one. Okay? This is what we want to do. And so we realized that, okay, what does a constant Hamiltonian look like in this picture? A constant Hamiltonian means that I map the entire torus into a fixed vector. So, the entire torus is mapped into a single vector. Do you agree? Okay. So this is just purely constant Hamiltonian. Okay. Let's see what else would be homotopic to this Hamiltonian. Okay? Suppose I had my torus, and instead of mapping every vector to a constant vector, suppose I mapped the image of this torus was, something that's kind of contained in like a small region. So suppose the entire torus got mapped, into various vectors in here. By this is h of k. So, do you agree? Is this can I write down some homotopy that will make it homotopic to this? I should be able to. I should be able to kind of, take this whole region and somehow like squeeze it down to a single point. Okay, I think you can actually write down like some explicit linear homotopy for this, actually, but it would need to be like in spherical coordinates. Why can you do this? Why can you do this? Because if I that's right. So if I because this is only for a a small patch. Do you agree? I can choose local coordinates for the sphere. Do you agree? So I can actually write down this green region as a piece of R2, okay, and then map it into the sphere nicely. Do you agree? But then if I map a torus into R2, do you agree? Then what can I do? And here, let's pick a random point here, I don't know, whatever it is, x. And so this is like, I don't know, call this f of k, whatever it is, f of k, and then this is, I don't know, phi, some coordinates. The point is that here, I can come up with the following mapping: f of tk is going to be 1 minus t f of k plus x, plus tx. Okay. What does this achieve? This achieves, at time equals, so I'm assuming this region is connected, but actually this region has to be connected because this is connected, so that's okay. I get what? Actually, not, it's connected and compact, so I think here, I think this has to end up being, actually, this might not be convex, so maybe this fails. If it's, it doesn't matter, even if it's not convex, no one cares. So the point is, as I increase t, do you agree? As I increase t from 0 to 1, at t equals 0, this function is just f of k. Do you agree? But then when t reaches 1, this function is now just a constant function x. Do you agree? So this just kind of takes this and over time just squeezes this whole thing into a single point. Do you agree? And it does so in a smooth way, because what's more smooth than a linear function? Okay? And this I did in like local coordinates, and then I can take this and compose it with phi and get something that does the same thing but on the sphere. Do you agree? So what's the key thing that I was able to use just now? What was the important part about this green piece? Like, why does this work?
It's local.
It's local, but it's not just that it's local. It's the fact that I can choose what?
Coordinate.
Yeah, I can choose coordinates, a coordinate patch, which fully encloses, this guy. Do you agree? So from this is like, actually, this is essentially a proof, as good a proof as anyone who does topology will ever write for you. Right? I get that if the image of H is a strict subset not equal of the torus, right? So if I can choose some local, if I can choose some coordinates where, if I can just choose some coordinates for the sphere, right, which are just R2, and so some coordinate patch that fully encloses this, then I realize I can just linearly interpolate this to a constant function. Do you agree? This implies that this Hamiltonian is homotopic to constant Hamiltonian. Okay? Oh, this is okay. This is if someone wants tea, they can get. They can have tea. Constant Hamiltonian. So that's not legible at all. Okay, we're halfway there. After this, I'll just kind of write down, kind of quickly, the Haldane model, and then. Do you agree? So I want what? So for something non-trivial to happen, for something non-trivial, I want h of k from the torus to S2. I want it to be such that the image of this map be the whole sphere. Do you agree? It has to be the whole sphere. Okay. People agree with this. So if the image of remember the Hamiltonian was h of k dot sigma, right? And I realized, wait a second, I can always, if there's a gap, this is always homotopic to h of k twiddle dot sigma, where this is just a unit vector on the sphere, in R3. Okay, so on S2. And I realized if I don't want this to be homotopic to something constant, then this h of k should cover the whole sphere. So for every point in the sphere, there's at least one k, where h of k gives me that point on the sphere. Otherwise, I can kind of do this trick where I can, it's defined in some region of the sphere, and I can like contract it to a point, and this will be homotopic. Okay, do you agree? Very good. So now we have to write down a tight binding model where the h of k gives me the whole the whole sphere. The image is the whole sphere. And I want it to be a two-band model. Do you agree? So two-band model. Yeah, and so now we'll write down the Haldane model this way. At least we'll realize what should happen. And then we'll realize what should happen, like make an educated guess, and then trust that if we actually did the calculation, this is what you would get. And of course, I did the calculation, but I'd still need a moment to check that the thing works, but that's okay. So, need two-band model. Need two-band tight binding model with h of k divided by norm h of k to cover sphere. Do you agree? So we have to start somewhere. First of all, I need a two-band model. Do you agree? So I need, how many atomic orbitals do I need to have in my lattice? If it's a two-band model. Remember we had the alpha, the basis was alpha m, right? And then I do alpha k, right? And when I write the Hamiltonian in this basis, the Hamiltonian was sum over k of some h of k's. And what was the basis of this guy? It's fixed k, but then what could vary? There's two letters. What's the other letter that's not k? What's the other letter that's not k that I'm pointing to? You don't need to look at your notes. You can just look at the board. There's two letters. One of them is k, the other one is not. Alpha. What did alpha mean? Do you remember? In our tight binding models? This state alpha m was the state for the
alpha,
yeah
the alpha atom within the unit cell?
Within the mth unit cell.
Yeah.
That's right. So when I write down the Hamiltonian momentum space, I could write it as some of these hk's. But the basis of these hk's are the alpha k's, where k is fixed and alpha can vary. So the type of atom can vary. So if in momentum space I want a two-band model, how many flavors of atoms do I want? I want
Alpha?
Yeah. But how many? If I want a two-band model, how many types of atoms do I want? Two, exactly. So I need lattice, and I need a 2D lattice with two types of atoms. Okay. Can someone give me a 2D lattice with two types of atoms that's really famous? Everyone talks about it all the time. Hmm?
The
Graphene. So we're going to arrive at what's called Haldane's model. I think Duncan Haldane came up with this, And it's really, all it is a modification to graphene tight binding. Modification to the graphene tight binding model. Okay? Very good. So let's remember what the graphene tight binding model was. And kind of quickly go through the motions. I think we've seen it once, maybe we've seen it maybe half a time, but that's okay. So I'm going to draw what? I'm going to draw the following. Oh, this is from QTS2 on Tuesday. Okay. So graphene, it's some honeycomb lattice. Do you agree? And the point is what? The point is that there's two sites. I need to tell you what's happening on two sites to explain what's going on. So I need to have these sites and these sites. These are my two types of atoms, right? And then I can, yeah, I think that's visible. These are my two types of atoms. And let's see. Yeah, that's right. So let's call the red ones A and the green ones B. A and B types of atoms. Okay. And okay, I will now do what? I will now allow hopping from. Let's start with nearest neighbor hopping. Do you agree? Meaning that what? Meaning that I can go from this guy here, here, or here. Okay? Do you agree? Okay, that's one thing. Oh yeah, I also forgot to mention that I get this lattice, given these two vectors, I get these lattice using the following lattice vectors. I'm going to have A1. This is going to be my A1, and this is going to be my A2. Right, so any 2 points connected by these lattice vectors or some linear combination of them are from the same sublattice. Yeah, like this, like this, like this. Okay, and then the other ones are going to be green. Okay? Do you agree? So I can generate the entire lattice by taking this pair and translating it by these two lattice vectors anyway. Okay. Good. Right, and so now I'm going to start with just regular tight binding model without modification. We're going to see what h of k we get, and then try and come up with a way to modify it to get something more interesting. So, good. So I'm going to say, okay, tight binding, nearest neighbor hopping. So from A, I can jump to some B sites. And let's say that these are going to be at, say this vector is delta 1, this vector is delta 2, this vector is delta 3. Do you agree? I'm just going to call this vector, this vector, this vector delta 1, 2, 3. In that case, let's write down the H kind of nearest neighbor hopping, the Hamiltonian for nearest neighbor hopping. We're going to sum over the unit cells. So I'm going to sum over some unit cell indices. Okay? And I'm going to do what? I'm going to allow hopping from with some amplitude minus t from into the B site atom. Yeah, into the B site atom with hopping at position, which position? In position in the unit cell. Well, yeah. At position m dot a plus delta j, plus delta j, and then I will be hopping here from the 8th type of atom at position m dot a. Okay, and I need to sum over the m's and the j's. Do you agree? So I'm summing. I go at each unit cell. Okay, to each unit cell. In each by unit cell I mean like each pair of atoms like this. Okay, and then I look at the red atom, right? So the 8th one, and say, aha, I can start at this one and end up at the one in B that's at m dot a plus delta j. So I can go to this one, or this one. And I add up the terms for all of them. Okay? And then I need the Hermite conjugate. So plus I need the Hermitian conjugate. Okay. There's so here I wrote it in kind of bracket notation, but I can also write this with C daggers, C whatever. So maybe let's write it like this. It's maybe a little bit easier. So M J, a B dagger, M dot A plus delta J, A annihilation operator like this, and then plus the Hermitian conjugate, which is just A dagger, M dot A, B, M dot A, plus delta J. Okay, do you agree? Okay. And now I want to write down the Fourier transform for B, write down the Fourier transform for A, and write this all in momentum space. Okay? And so I'm going to do this kind of quickly. So yeah, I'm just going to do this kind of quickly. So recall that the Fourier transform of Bj was equal to Bj dagger was equal to e to the minus I k dot bm dot a I k m dot a plus tau beta. Okay, I need to sum over all k's, and then times bk dagger. Yeah, and there was a minus here because there was no minus for this one. Good. And then I have a 1 over root n, but it drops out at the end. So that's right. Okay. And so now I'm going to, you know what? Yeah, we have a bit of time left. I'll write it out properly for this one, and then for the next time we compute this, I will. So minus t, okay. I'm still summing over m. I'm summing over over j, but now I need to Fourier transform this guy and this guy. So I'm now going to have a sum over k and k prime, one for this guy, one for this guy. Okay, do you agree? I'm now going to have a factor of 1 over n, because I had 1 over root n. I get 1 over root n for each. I get 1 over n. And now I do what? I replace this guy with this, and this guy with the same expression, but this. Okay. I'm also going to set tau alpha to be 0, so that the red atoms are at 0, 0 coordinates, and then the beta atoms are at whatever tau beta is. Okay. Do you agree? Good. Good. And so now let's write down the exponential factor. So from the beta I get e to the ik minus ik dot m dot a plus delta j. Do you agree? This is from the B1, because m dot a plus delta j, that's the exact position of the bth atom. So that's what I plug in there. Okay. And then I get plus ik prime dot m dot a. Do you agree? Because this is the factor I get from the a thing, right? Because the a thing is not a conjugate, so not a dagger, so it doesn't have the minus over here. So it has a plus, and so that's right. And then I'm left with b dagger k, ak. Okay, and then plus Hermitian conjugate. Okay, but now I can rewrite this as e to the I m dot a k prime minus k minus I k dot delta j. Do you agree? And then times the same thing. And now if I can do the sum over m, right? Because I can kind of factor the rest out. The rest doesn't depend on m. And remember that gave me a delta function. So I can just get rid of the sum over, doing the sum over m, sets k equal to k prime. Okay. So I'm left with, and then the 1 over n factor also goes away. So actually, is it okay if I erase this line? I think this line is, oh, erased too much. I am left with, I need to sum over j over k of e to the I k dot delta j b dagger k ak, and the Hermite conjugate is going to be plus e to the minus ik dot delta j ak dagger bk. Do you agree? Okay, very good. So now let's write this down in this h of k way. Okay, let's write this down as a matrix and as an h of k matrix. So this is going to be minus t sum over k times what? Okay, I'm going to have a dagger k, b dagger k, some matrix ak bk. And what is this matrix going to be? Well, look, I have ak to b dagger k, and I only have a and b coupled, not b and a. So I'm going to have 0, 0 on the diagonals. And over here, I'm going to have the sum over j of e to the I k dot delta j. Sorry, going from b to a. So this one has a minus, this one has a plus. Yeah, this one has a minus, this one has a plus. Do you agree? Okay. Yes? Actually, maybe I wanted it to be the other way around, and I think in my notes I made an error and I have it the other way around, but No, whatever, close enough. And so I want to write this as, the Pauli matrices, right? Something times sigma x plus something times sigma y. Do you agree? But this something is going to be precisely what? Precisely what? This is going to be equal to minus t sum over k, okay, this thing. And this is going to be what? This is going to be for the sigma x. Sigma x is what? 0, 0, 1, 1. Do you agree? So the sigma x is just going to be the real part of this sum. Okay? And the sigma y part is going to be minus the complex part of this sum. And then, okay, the sigma z part is 0. Right, because I have nothing on the diagonals. Do you agree?
Why is the real part an imaginary part?
Because, so good question. Remember, sigma x was 0, 0, 1, 1. Sigma y was 0, 0, I minus I. Do you agree? So I want to write this matrix down as real number times sigma x plus real number times sigma y. Do you agree? So real numbers. This is what? This is just, okay, this sum is whatever. Its sum at the end of the day is going to be sum a plus bi. Do you agree? And this is going to be the complex conjugate of this sum. This is going to be a minus bi. Do you agree? So if I do a times sigma x, I get AA. And then if I do minus b times sigma y, I'm going to get a minus bi plus a plus bi over here. Do you see this? Yeah, so this is why. It's just like, I want to write this as something times this plus something times this. And so you see that this something has to be the real part, this something has to be times the complex part. That's it. Okay, so there's a few issues with this. Okay, and so this is this sum over j. Remember what these delta j's were. These delta j's were, the vector from here to here, from here to here. So it's just 3 vectors. Do you agree? This is a sum over 3 vectors. You can do this by hand. This sum, and look at the coordinates. In fact, I did do this by hand, but on Mathematica, but then I have a sign error. So, okay, I'll write this down maybe on the next board. Good. So there's a few problems once you compute this. So the first thing, can you immediately tell me if there was no other problem that I haven't mentioned yet, can you immediately tell me if this is going to be trivial or non-trivial? Remember, for it to be non-trivial, the map has to cover the whole sphere. Okay? Does this cover the whole sphere? And if not, why? What is one point on the sphere that this map can never reach? So this vector is always of what form? There's something in the first component, something in the second component, and what is in the third component? Always 0. Okay. What's a vector on the sphere that has, non-zero last component? I don't know. Any vector.
It's not at the center, is at the other.
Yes. So whatever I get with this will always be a vector that's kind of like on the equator, right? But if I just have something on the equator, I can always, homotopy it to a constant degree. So this doesn't cover the whole sphere. What's worse is that this doesn't even have a gap. Do you agree? This does not have a gap. Yeah, it doesn't have a gap.
For a while?
If you compute this out, if you were to actually compute this and plot this, okay, let me take a picture and then I'll erase this and then write on the next board.
So if you have like the real square plus the imaginary square, so it's just the magnitude.
Yes, it's the magnitude squared, but that magnitude can indeed go to 0. This vector can go to 0 if you compute it out, and I'll show you what the computation is. I will erase this. So I'll just keep the condition in. I'll keep the condition in the corner here. Remember that need the image of h of k to be the whole sphere. Okay, so I need to have like non-zero components everywhere, and I need them to really vary around so that I kind of hit every direction possible. Do you agree? So, what was the point? Okay, so if you compute this out, I think what I have is roughly correct. So, like it's correct up to it being wrong, but that's okay. So h of k in this case is cosine of akx over root 3 plus 2 cosine akx over 2 root 3. And this is maybe not the best way to write it. Like it's not obvious that this that this can go to 0 at some point, but it indeed does. So this is the sigma x component, and the sigma y component should be. I should have a minus, I think, right? So I should be minus I just minus of 2 cos aky over 2 sine akx over 2 root 3 minus sine akx over root 3 and then common 0. That is correct. Yes. Yes. And I think the eigenvalues then should be plus minus something like this. 3 plus 4 cos root 3 over 2 akx cos aky over 2 plus 2 cos aky over 2. Okay? And this I think you can actually read off kind of in a straight forward way maybe. That, you know, if I picked ky such that maybe this cos ky is minus, I don't know, minus half, let's say, or maybe minus 1, right? This is going to be negative. This will cancel most of this, right? This will be, let's say this is minus 1/2 at best. You know, I should be able to pick a kx to make this whole thing go to 0, right? Like, you can believe me that this is 0. And it's also, this is like a well-known fact, that the graphene has Dirac cones, what people say Dirac cones at the k points. So if you drew the Brillouin zone, it's going to be some sort of hexagon as well. And the point is that the the energy dispersion will like kind of go to zero. I'm trying to draw the surface. I don't have a good plot, but the point is it goes to zero at the k points, at these points in the Brillouin zone. And I mean, you can check that, check what these points are, compute them. So this is k space, momentum space. Okay, this goes to zero. Okay. So first of all, this Hamiltonian, we need to modify it. So first of all, I add a gap, that's part A, and part B, this Hamiltonian has to kind of go over the entire sphere, right? So this vector h of k has to go in every direction possible. Okay. How are we going to do this? Well, you know, the fact that there's no gap is one thing, and then I also don't have a sigma z term. So hopefully, if I took this guy, and then I added some sigma z term, do you agree? Then I'll have more stuff, like something else squared in here, right? I'll have plus h3 squared, right? So that would be good. You know, I'll get a gap, hopefully. And then hopefully this doesn't go to zero at the same time as this part does. And that should be easy, because it goes only to zero only at a few points. So that shouldn't be too hard. And then the other thing is, if I had an sigma z term, right, then this should really kind of, if it was also momentum dependent, right, then maybe that would help me kind of point in various sorts of directions. Do you agree? Okay. Now, how does this h3 term have to look like? Well, the contribution to the Hamiltonian has to be, you know, some h of 3 of k minus h of 3 of k. Do you agree? So it has to be something where the A hops to another A and the B hops to another B. Do you agree? But they have to hop with opposite amplitudes. Okay. How am I going to achieve this? Okay, well, okay, I have to, you know, I can see that, okay, A has to hop to A, B has to hop to B. So let's start with that, okay? So I need the, do I want to redraw this? Yeah, let me redraw this. This is gonna, bear with me, this is gonna take me another moment. We're almost there. This is like practically the end. Okay. Agreement. Good. So this was my red, this was my green. So let me do all the reds. Okay, and all the greens. Okay, so now I'm saying, okay, I should allow, there should be some hopping from A to A and from B to B. Do you agree? This is for a sigma z, that's what I need. So, okay, let's look. What kind of hopping do I already have? I already have this kind of hopping. Do you agree? But then what do I need? Okay, now I want A to A hopping. Okay, I could do just A to itself, but that's just going to give me some constant term. That's not going to be momentum dependent. Why? Because remember, how did I get this momentum dependence? Do you agree? It was when I did the Fourier transform, I had these exponentials, and I realized that there was like, so I was hopping by some vector delta j, and then the contribution was e to the I k times the vector in the direction I was hopping. Do you agree? So I need to be going somewhere non-zero. Okay. So what are the, so let's hop to the closest points. So I should have hopping to the next nearest neighbors. Do you agree? I should hop here, 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 and here. Okay, so I should do this. I mean, it's just the next thing to try, right? And then the same thing should be for B. Do you agree? However, I want something particular. I want the hoppings for the A's and for the B's to have opposite sign. Do you agree? But also, in some sense, the hopping should kind of look the same, right? Because the lattice, I should be able to like reflect it and kind of get the same thing. Okay? So how am I going to do this? Well. Remember that when I wrote down this term, I had a Hermitian conjugate. Do you agree? Which had some kind of, it was the complex conjugate of this number, of whatever this number was. Okay? But whatever this number was, this really includes the minus t. Right? Before I didn't write it in the complex conjugate because t was a real number necessarily. Okay? Suppose we took t to be a purely imaginary number for these hoppings. Do you agree? Then, when I take the complex conjugate, I'm going to get like a minus sign on the Hermitian conjugate. Okay, that's going to be good. But then perhaps I can do something about the direction of the hoppings, such that the direction of the hoppings is for the A's is somehow opposite of the one for the B's. Okay, so that maybe doesn't quite make sense. I'm going to draw a diagram, and I'm going to complete this diagram, and it's going to make sense. So I will say, okay, I'm going to draw arrows this way, this way, this way, this way, this way, this way. So as you can see, the arrows, the way I drew them, I always have like vectors going clockwise. Vectors going clockwise. Do you see? And now I'm going to say that I hop clockwise to second nearest neighbors, next nearest neighbors, with amplitude IT2. Okay? Yeah. But this means what? This means that from here, I jump with IT2, but when I jump back, I will jump with minus IT2. Do you agree? But now, look what's interesting. If I use the same rule for the green sides, the green sides are going to have what? It's going to be like this, like this, like this. Do you agree? And so, like this, and then here it's going to be like this, and here it's going to be like this, and then like this. Am I missing anything? No. Okay? Do you agree? So look, for the red sides, hopping up was IT2. Do you agree? For the green sides, hopping up is minus IT2. Do you agree? Because I'm saying that the direction of the hopping with positive IT2 is the direction of the arrow, and then the opposite direction is, okay, so whatever. Good. Do you agree with this now? Okay? And so now this will give me precisely the right thing. Because here, hopping this way is positive, but here hopping the same way is negative. So you can see how I'm going to get some positive hopping amplitude for these, and then some negative hopping amplitude for the B sides. Do you agree? And so, for example, if I say that, so for the red one, let me define all the vectors to be, so the 6 vectors to be, gamma 1, then say with gamma 2 I hop away. So gamma are going to be all the vectors where I hop away, and then let's say gamma twiddle are going to be the vectors with which I hop towards the point. So away from the point and towards the point. Then H next nearest neighbor I'm going to once again sum over all sides. But now I'm going to do what? I'm going to sum over, okay, I'm going to sum over, I don't know, let's take some index p. And I'm going to hop with it. I'm going to be hopping away from the A side. Do you agree? So this means this is going to be a dagger m dot a plus gamma j dot a m dot a. Do you agree? So this is over gamma j, this one, this one, this one, where I'm hopping away. And then I'm going to have minus it, a dagger, m dot a. So I'm with these ones, I'm going to be hopping towards the point. Times a m dot a plus gamma twiddle j. Okay, and then plus Hermitian conjugate of this whole thing. Okay. But then for the B sites, this is T2. I'm going to have the exact opposite. For the B sites, I'm going to have what? For the B side, so remember, here hopping away was in this direction. Do you agree? But for a B side, this is hopping towards. Do you agree? So this is going to have a minus it2 b m dot a plus gamma j b m dot a. So it's like for the B sides, hopping in the gamma j directions is kind of like this term. Do you agree? Because for them, hopping this way is actually hopping towards and not hopping away. And so then this is going to be it2 b dagger m dot a. Oh, sorry, this should be like this and like this, and then this should be a twiddle, and then this should be like this and like this. Okay, and then I should have Hermitian conjugate. Okay. Yeah, so this term is this term, this term is this term. But with, the sign here is positive, here is negative. Okay, good. Sorry. I should have written it. I should have written this term here and this term here, so it's less confusing. You know what? Sorry, I'll actually forget about this for a second. But this, I'm going to correct this. This has a minus. This has plus delta j. This has a plus, and this doesn't have this. And then this has plus delta j like this. Okay, like this. Okay. And you can see that this is minus of this term, this is minus of this term, but I replace a's with b's. Okay? But the gamma j's are the same. So that you can see that when I Fourier transform, I'm just going to have some sum of e to the I k dot gammas, and then this is going to be minus sum of e to the I k dot gammas, where I sum them with some particular rule. Okay? And so for this, you can use Mathematica to compute that this contributes an H3 term of, I think I have the minus sign correct. Maybe I don't, but that's whatever. Okay, whatever. Plus minus 8 cos root 3 over 2 akx times sine aky over 2 plus sine aky. Okay. Good. And so now we get a non-zero hz term. You can check that, well, it's kind of hard to check, but you can believe me that whenever this is 0, this is not going to be 0. I mean, you can also do this by like just checking that it's 0 only at these points, figuring out what those points are, plugging those points into here, getting that this is not 0. Okay, so I get a gap first of all, and second of all, it is you can also check, and I'm actually not sure this would be much more tedious to check by hand, but you can check that this will not this moves around in different directions of k, so this will hopefully kind of cover the entire sphere somehow. Okay. Alternatively, the stuff that we talked about with the Chern number before, this does define you a Hamiltonian. Given a Hamiltonian, I can compute these connection things. I can compute the Chern number. It's a bit tedious, but you get that the Chern number for this kind of system is plus or minus 1 if T2 is non-zero. Okay. Okay. And so this is what's called the Haldane model. This is, I allows complex nearest neighbor hoppings. And if I do that, then I get these, non-zero Chern numbers. I get some non-trivial band structure, which is not homotopic to the identity. Okay. Oh, to a constant map, not the identity, a constant map. Okay. And so this is indeed an example of a type number. Now, I'll make one last comment. You might say, okay, complex hoppings. How is this even possible? What does that mean? Okay. That is actually possible. I think are some materials that aren't quite like this, not quite honeycomb lattice, but they do exhibit. They do have a tight binding model with some complex hoppings. Complex hoppings, what could give them? One way you can achieve them is having a magnetic field. If you had a magnetic field, then your hoppings acquire some phase, because your electron is like traveling through a magnetic field, so it's like rotating. So it gets a complex phase when it hops. That's one way to do it. But the crazy thing is that in principle this is possible without any magnetic field if you just found some other way to get a complex hopping. One way they've done this, which I've not had time to read about properly, but they had this experiment. I think it was like some cold atom experiment where they can really engineer this more carefully. But the idea was kind of stupid. They just took their lattice and they started shaking it at some frequency, like just moving it, up and down. And there, like if you have, certain kind of shaking, whatever, you can just write down the expression for the hoppings because the lattice is being shaken with some frequency omega, and then you can do like some expansion of some sort. And in that approximation, those hoppings acquire like just a complex number because you have periodic shaking, which it's some e to the I t omega whatever, and so that appears in the calculation somehow. I'm not too familiar, but you do some expansion and you get like just complex hoppings. The hoppings aren't like purely complex, but they have a complex piece, and we did this calculation for a complex piece. For their complex piece, you do get an H3 term like this. Okay, and then they'll have some usual, some like more constant term, like sigma 0 of k. But that's okay. And so they actually have done this experiment, I think in 2014, where they took a lattice, shook it, and then they were able to see like this. I think they were able to see these edge currents in this model, and I think they actually had some way where they measured the Berry curvature directly. I don't know how they did that, but that's also something they did. So Haldane model has been experimentally, they cooked it up experimentally. There are, however, like more conventional like materials where it's just a material that has a tight binding model that describes it that is not trivial. But this is kind of the first thing that people thought, one of the first Chern insulator that people came up with. The other thing is, not only is this a Chern insulator, because you have like these currents only at the edge. This is Haldane came up with this in context of the quantum Hall effect. The quantum Hall effect, remember, is that the resistance, the XY resistance, is quantized. Do you agree? But here I get that this is an insulator where I can only travel around the edge depending on where I am, and the edge current is quantized in terms of this Chern number thing that we talked about before, and so that sounds exactly like the quantum Hall, right? Where I can I have some way to get from x to, from one side of the sample to the other. In this case, it's by going around the boundary, and this can only happen in like some integer amounts of the Chern number. So this is also captures quantum Hall physics in some sense. And here's like just we came up with a particular tight binding model, the Haldane model, that does this. There's other tight binding models you can cook up, but this is the first one people thought of. Okay, I think this is it. We started a bit late, and so we ended a bit late, but this is it.